we're going to find the gravitational field, little g, at this point due to a bar of mass m and length L. We are going to find g for this entire bar. Well, you should already sense that the issue is this little mass here, let's take a little bitty mass here, it's going to have a gravitational field, but the closer part of the bar will pull on it stronger because it's closer. So what we're going to do is we're going to add up this one, this one, this one, this one, this one, which of course is the purview of calculus. So what we do is we define a very small dm. And as we know, if you can find a small differential and add them together, you get the whole thing. So what we're actually going to do is this. If we can find dg, an infinitesimally small gravitational field, and if we take the integral of it, we will have the total gravitational field due to the bar. So what do we have to do? We have to define dg. Well, let me see. Our equation for g, well, let's just start with dg is going to equal big G, and instead of m over r squared, it's going to be dm over r squared. Pretty straightforward, right? So we need to define r. You'd agree that r is a variable. And we're gonna add up this little dm here and all the little dm's from 0 to L. This is how far we're going to add. And we'll just call this, we either call this, I guess we could say L equals 0 and L equals big L. And we're gonna, as I used to, I don't know why I think of it this way, we're gonna sweep from one to the other and we're gonna add them all up. Well, R would be this. And this distance right here, we're gonna call L. We could call it X, whatever, okay? And as you can see from here, yeah, this is going to be easier if we use the little x, I'm sorry. So, just because that's an x naught. And the books use an x. So, would we agree that x plus r equals x naught? Okay, so let's put over here so we have our information. We have x naught equals x plus r, therefore r equals x naught minus x. Hey, now we have r defined as x. However, this little dm is not defined as x. But we just learned that we can do this by taking the line density, which is defined as kilograms per meter, or the total mass divided by the total length. Which is what, and since lambda, the density, is a constant, it would also equal dm over, instead of dl, we're going to call it dx. So we now have found that dm equals lambda dx, and that really is the trick. If you didn't know how to do this, this problem would be impossible. That's actually the trick. Okay, so now we plug all of that in over here, and we get dg equals, well, big G is still a constant, dm is now lambda dx, and r is r naught minus x squared. And as we look at this, we can see that there's only one variable. G is a constant, lambda constant, x naught constant. And we have x, dx, and x. And if we take the integral of this, we would get the total. So let's do that. We are going to take the integral of all of that, big G, lambda, dx, over x naught minus x squared, I believe I got that right, and we're going to add them up from where x equals 0 to x equals L, the end of the bar. And that will give us G. I see a constant and a constant, and of course they come out of the integral. Now let's read this notation. Let's make sure we are reinforcing this at every step. This says, take the antiderivative of the function where x is the only variable. Now, hopefully we remember from stuff that we did previous this year that there's a way to deal with what we have here, and it's called u substitution. We're going to let u equal x naught minus x. Then du, well, the derivative of that is just 0, minus dx. So dx equals negative du. Now, I want to talk about this idea of going from here to the differential just real quickly. This is kind of a strange thing, and let me do this a little bit more in the usual manner to prove that this works. Would you agree that if u equals x naught minus x, I want to take the derivative with respect to x. And when I say derivative with respect to x, take the derivative where x is the only variable. So, du dx would equal 0 minus, and does that become negative 1? Then I solve for du, and du equals negative dx. I just skipped the du dx thing here to get to this point. Do we see how that proves it there? Okay, so now we've defined u and dx, and we're going to substitute them in. So now we have, I'm going to do it up here so that I have enough space. G lambda, and I'm just going to ignore the limits. I know that for technically, if you're doing this in calculus, you're supposed to change the limits, but we're going to bring it back later on, so this is not a problem. So we know that dx equals negative du, and this is going to be u squared. Again, the negative comes out of the integral, and we get negative g lambda, and this will be the integral of u to the minus 2 du. Well, what is the antiderivative of u to the negative 2? Add 1 to the power, subtract from the new power, which gives me negative g lambda, add 1 to the power, subtract by the new power. Some people have been asking, where did the du go? Just as when you're doing multiply or division, you've got that line. When you take the division, the line disappears. Likewise, this is only telling you, take the antiderivative where du is the only variable. Once you have done that function, they disappear. Okay, so where do they go? We took the antiderivative. They're gone. Okay, so now this gives us g, but now we also have to remember, oh, we were going from 0 to L, which is going to come back here in a second. So now I have g equals, you see how negative 1 minus 1, right? So that's going to give me a plus 1, or I mean a plus g lambda. That was silly. And then I'm now going to take, would you agree, u to the minus 1 is the same as 1 over u, but I'm going to put back in what u equals, which is this. And I'm going to evaluate from 0 to L, which means, remember the x final minus x initial? X stood for the function. So it's going to be the function with the final amount minus the function with the initial amount, which gives me g lambda 1 over, that's a constant, minus L, minus this with 0 in for x, which is just x naught. Now I'm going to do common denominator, which is multiply them together. And so if I multiply top and bottom by x naught and top and bottom by x to the minus L, we good on that so far? I'm going to get, can we still see this all right on the video or not? Okay, so we're going to get g lambda x over x minus L minus x minus L over x, oh, sorry, common denominator, that was very silly, sorry. So it's going to be x naught minus x naught minus L over the multiplication of the two. I'd really rather not. Okay, so now let's take that. Can you still see me down here? Okay, so notice we have x naught minus x naught. Do we see that? X naught minus x naught. So that gives me g equals g lambda. The x naughts cancel, and I just get, oh, and a negative of a negative L is a positive L. And on the bottom, we get x naught minus L. And then we look at this and say, oh, from up above, this is just m divided by L, which gives me g m divided by L, L over x naught x to the minus L, sorry, that's a naught. And because I don't want to be on my knees too much longer, and I'm going to come over here, that gives us a final answer of, well, I'm not going to put that. G equals, see the L's cancel? And we get G M over x naught minus L. And that's our final answer. Once again, as a recap, the most important thing that most people don't know how to do is this with the line densities. Also, in all cases, we're going to start with a little dg from a small little dm, and we're going to calculate g. Now, in some cases, as we did in a previous example, we're finding the potential energy of the bar. Sometimes, in order to understand things, we start with known things, things that are relatively easy. We do it a different way, and if we get the same answer, we know we did it right, because physics always agrees. You can go different directions, and you will still get to the same answer. If not, either your methodology is wrong, you made a mistake, or you have found an inconsistency in physics, which at this point is pretty, not going to happen. Okay?